Today we want to talk about error analysis and data processing, and so let me get started with that. First of all, we need to talk about error, but error is a short word for uncertainties in measured quantities. So whenever I say error, please in your mind think uncertainty in a measured quantity, because that's what we do in this lab, is measure a bunch of things, process them in some way that theoretically involves an expression, a law, F equals ma, these kinds of things, and then see if it works, see how close to the accepted answer, because this is an introductory lab, and obviously it's been done before by hundreds, if not millions of people, and so we're not going to discover much new here. However, we need to know how to process our data and compare it to either a known value, or if we know it, or some other value. If we don't know it, then we're doing frontline research, which means coming up with the answer for the first time ever, which makes error analysis even more important. Error. This is my handwriting, I'm sorry about that. But error means the uncertainty in measured quantity. So, again, we're going to stick with the word error for short, but you know what we're talking about. So our job is to measure things and figure out how good our measurements are. Probably in high school, you measured a bunch of stuff, you put your values or averages or whatever into a formula, and for instance, F equals ma, everything like that, and you figured out from a certain mass and a certain acceleration what the force on something was. Fine. That's half the problem. Probably that's all the problem you're worried about previously. But we need to know the quality of these values. That is, how well do you know the mass? How well do you know the acceleration? And when you multiply them together, how well do you know the answer? That is, what is the percent error or the fractional error or whatever have you for this answer? So just an answer by itself without any estimation of the error in that answer, uncertainty in the answer, it's not enough. It's just half the story. Sometimes it's even less than half the story. There's two types of error. One of them is the easier one to work with if you know how to work with it, and that's the systematic error. And it's pretty self-explanatory. Systematic means it's the same every time you use that instrument. It's the same every time. So I have some interesting examples of that. Is this Garfield cartoon that my wife got some years ago, and it has to do with weighing yourself on the bathroom scale. And you know, Garfield has this weight problem apparently. So here's the Garfield cartoon. Okay, so you see Garfield's 5 pounds lighter than he is by adjusting the scale to -5 pounds before getting onto it. The last unfortunate example I want to mention for a systematic error was these meter sticks. Now, I bought these meter sticks 2 years ago, bought like 30, 50 of them, I don't know how many, and I didn't pay any attention to the ends of the meter stick. Of course, when you use a meter stick, we'll talk about that later also, do not ever use the end if you can avoid it, because you're assuming the end is 0 and it isn't. And in fact, on these meter sticks, the end is definitely not 0. It's 2 millimeters below 0. And on the other end is 2 millimeters above 0. So if you measure something with this meter stick, like a meter, it's actually 1.004 meters, which is 0.4%, which is probably not a big problem in most cases. But just be aware that this introduces a 2 centimeter, or if you use the whole thing, 4 millimeters, sorry, systematic error. So if you're aware of the systematic error, like I was here and Garfield was, except he wouldn't tell anybody, and I've made this adjustment on my meter, pressure gauge, you can fix it. So you have to be aware of it to fix it, which is so if you're not aware of it, it's a built-in error. It's going to be there the same every time you use that instrument, and you're stuck with it. And if you do your analysis and get an answer, it's going to be off by at least that much because you never noticed the error. So that's the good news and the bad news about systematic errors. Try to figure out if there is one by taking a close look, like I did with regard to the meter stick, at the meter stick or the instrument you're using and seeing if it really has a 0 at 0. Okay, the other error which we need to talk about, which is much more involved and much more prevalent, is a random error. And I'll label it as plus or minus. That is, when you measure something which has a random error, sometimes you get a value that's a little bit higher, sometimes you get a value that's a little bit lower, and of course, the secret to random errors is averaging. If you average a bunch of readings that you take, you will get a better and better value. That's the theory, and a value closer and closer to what we might call the true value. So we need to average here, which of course means you have to take more than one data point to get an average. And I would recommend typically at least 3 data points. So if you can measure the same thing conveniently, fairly easily, 3 or 4 times, please do that. Don't just measure it once. Now, a lot of you are going to be engineers, and I know you like to have fun with destructive testing. It is fun. And if you use destructive testing, you're not going to be able to get an average because you've broken it the first time, which is your job at that point. So all you can do there is take a bunch of the same things that are supposed to be the same and break a bunch of them and get an average breaking force or whatever it is for that particular rod or whatever it is. So averaging is the best way. And we're going to say that we're going to call the average the experimental value. In other words, it's the value, it's the best value, it's the best value. So it's the best value or the experimental value. So I'll probably use those words interchangeably as we talk about error analysis. Let me put in a commercial for measuring as carefully as possible with any instrument that you use. For instance, with a meter stick, these are centimeters, 100 centimeters is a meter. You can measure them. You can measure with this meter stick to the nearest centimeter. That's kind of crude. You can measure it to the nearest millimeter, which are the small markings. There's 1,000 of these marks from one end to the other. 100, not 1,000. And it can read in between the lines sometimes, literally. You can estimate if you have something very sharp, like a little point, such as we'll be seeing when we do a free fall experiment. You can estimate in between those millimeters to, some say, 1/10 of a millimeter. You've got really good eyesight, maybe 2/10, or maybe you can break it up into quarters or something like that, or at least halves. So you can get a little bit more than a millimeter accuracy with a meter stick, but you probably never had done that. So push every instrument that you're using to measure to its extreme limit, and it may be overkill, in which case you just don't worry about those last number or two. You'll find that out as you process the data, or it may be extremely important, such as it is on the free fall lab, whether it's point this or point that millimeters or centimeters. That end of commercial. Let's get back to analysis of errors, analysis of random errors. Okay, so let's say you do an experiment and you measure something, and this is kind of a crude experiment. You measure something 6 times, which is fine. If you do it at least 3 times, that's good. And you get the following values: 7.2, 7.4, 6.9, 6.8, 7.0, and 6.7. So those are your experimental values. And of course, if you average these, it turns out I made it this way just for convenience, you get an average of 7.0. So this, we are saying, is a much better value than picking any one of these, or any two of these, or any three of these. If you pick all six and you average them, you get the best value for that quantity, which is 7.0, whatever they are. Now, that's the part that you've already known how to do, you've already done, you've already used that in analyzing labs in physics before, I'm sure. But what we need to know now is how big of an error does this number have? How big of a random error does that number have? Well, there's two ways to do this, and this 6 values kind of is on the borderline between one or the other ways to use. If you only have 3 or 4 readings, for sure, you have to simply use the maximum deviation method of reporting this uncertainty, this error here. And the maximum deviation means, kind of what it says, the maximum deviation from the mean, from the average. So 7.0 plus or minus what? So you look at these data and you say, what's the number that's either most above or farthest below 7.0? And that's this one, 7.4. Sometimes it's the number above it, sometimes the number below it. It doesn't necessarily mean that the number above it, the maximum number above it, is the same difference from the average as the minimum number below it. So here it's 0.4 above and 0.3 below, so I'm going to use 0.4. Okay. So my reported value is 7.0, the average, plus or minus the uncertainty. So I'm going to say my measured value, that's supposed to be measured value is x average. The theory is the average value is the best value, plus or minus the uncertainty in x, in the value, whatever it is. So this is a little delta, which is the Greek symbol for d, which stands for difference, uncertainty, whatever. So this is my little symbol for uncertainty. It's typically used, delta. If you have a big uncertainty, maybe it's a big delta. Okay. In any case, it's a little delta here. So this is the way you report all your values, and you get this by this kind of analysis. The maximum deviation, so this is the maximum deviation. And it goes without saying, but I'll say it once, from the mean. It's the number that's farthest either above or below your average value. Okay. And that's, you kind of have to stop there with your analysis. Now, if you take more than 6 readings, 6 is kind of the borderline in my mind. If you take 10 readings, which you'll do in the lab next week very quickly, if you take 10 readings, 8 readings, 10 readings, whatever, more than 4, 5, or 6 readings, the other type of error is called a standard deviation. And we use the Greek symbol sigma for the standard deviation. That's typically the simplest. Okay, so this is a much more complicated thing. We're not going to get into the theory of it. That is the mathematical rationale behind all of this. We'll take another lecture. It's important. You can read all about this, and maybe you've read all about this in statistics textbook. So let's calculate the standard deviation of these numbers. And I'll do that by skipping the theory, which we don't usually like to do in physics, and define standard deviation. the 3 bars to me means defined, whatever. You don't have to worry about that. So the standard deviation is obtained by finding the discrepancy between the mean and each one of these values. So the discrepancy for the first value would be 7.2 minus 7.0, which is plus 0.2. So to get the discrepancy, this is the average value, and this is your experimental data point. Some of these are going to come out plus, obviously like this one, and some of them, these 3 are going to come out minus, because these numbers are below the average. That's what average is all about. So this is going to be plus or minus. Now, if you think about this, if you take all these discrepancies and you add them all up, the ones that are above the average and the ones that are below average are going to basically cancel out. They're going to add up to 0. The discrepancies are going to add up to 0, and so that's not going to give you anything, because that always happens. That will always happen when you do this. So what we do then is take the discrepancy, and what we do is we square that. That gets rid of the sign, and that tells you just the absolute value of how far off from each one of the numbers this is. And then we have to add those all up. This is big sigma. And since we've squared them, we have to take kind of the average of that. And there's a sample standard deviation, and there's the regular deviation, and the difference in the two basically is the number that's downstairs, and this is the number of trials. Just to be safe, if you take 5 readings, this number would be 4. If you take 100 readings, this number would be 99. There's not a whole lot of difference between 100 and 99. It's a 1% difference, but there's a 20% difference between 4 and 5. And so we want to err, that's ERR, we want to err towards the high end of the error range. And so this ensures that if you have small numbers, this is going to be a little bit bigger otherwise. And then, of course, since we square this, and we're kind of taking an average of the error squared, we've got to end up taking the square root of that to get back to the first power, the first order. So this is the definition of standard deviation. It's the sum of the discrepancies squared to get rid of the minus sign so they don't average to 0, divided by n minus 1, where n is the number of trials, number of measurements you took, and that gives you an average squared discrepancy. When you take the square root of it, you get the standard deviation. Okay, so that's the definition of the standard deviation. So let's do that. I'm not sure I'm going to carry this all out, but so sigma here is equal to the square root of 7.2 minus 7.0 squared plus 7.4 minus 7.0 squared plus, and I'm not going to do all the others, some of them plus, some of them minus, again divided by 6 minus 1. Okay, square these all out and add them all up. So this is tedious. There are programs in your calculator, for instance, or on a computer that can do this quickly and automatically for you. If you want to read on page 54 or whatever is for your manual for the calculator, they'll tell you how to do that. So I'm just going to say that I've done that, which I have, and I've done it actually the hard way by getting these 6 terms, which are all pretty small. 0.2 squared is 0.04, 0.4 squared is 0.16, so we have small numbers there. Add them all up, divide by 5, and then take the square root of that. So you get a number that ends up to be 0.3. Okay. So remember over here, we got 0.4 for the maximum deviation. This is 0.3. 0.3 is 3/4 of 4, obviously. And so the theory, if you take a lot of data points and take the standard deviation of lots of data points statistically as the distribution, as the number of readings you take goes towards infinity, and the limit, as they say, you get the fact that the range of standard deviation ranges from your average value plus or minus 68% of your readings. Now, the maximum deviation, of course, includes the 100% of your readings, because that's the way you define the maximum deviation. But this only includes roughly 2/3. This should come out roughly 3/4, and the limit of large numbers, about 68% of your readings are included in this range. So you have your average value, and you have a range here, plus sigma and minus sigma, and 68% of all your readings fall in that range. And it's called a double Gaussian curve. You've probably seen this before. So this would be your average value. Average value is the best value. It's the most probable value. If I look at it this way, there's a probability distribution, and 68% of the values fall in here. Your maximum deviation would be over here and over here. That is, includes everything. That's what maximum means. So, but 2/3, roughly 68% of the values are going to be from sigma, from your average value, plus sigma, to your average value minus sigma. Much more sophisticated, much more definite uncertainty, if that's not a contradiction in terms. And typically, now this is an introductory course. You only have so many hours, 1 or 2 hours at the most, to do the experiment and do the analysis and so forth. So we generally don't want to have you take many readings to have this wonderful, beautiful distribution and get a great standard deviation that you can really hang your head on. But so if you were to do this for real, for publication, you'd want to get as many data points as you could to get a more definite standard deviation that you can be reliant on. But the problem is, in physics, in the real world, your job is not going to be to get the best value for one thing and call it quits. Your job in the real world is to put things together experimentally and come up with a result that fits some sort of hypothesis or some theory that you're trying to find out if it's right or not. Or maybe, if you don't even know what the theory is, if you're in the front edge, cutting edge of research, you don't have the answer. You're looking for the answer. And then that's where the standard deviation and the error analysis becomes extremely important, because you need to convince the next person that this is the number you got, and this is how far away from the real true number it could be, which is your standard or maximum deviation. Let's say, I mean, there's only 4 basic things you can do mathematically. You can add, subtract, multiply, and divide. I mean, yeah, there's logs and exponents and so forth, but they basically trace back to their origins to adding, subtracting, multiplying, dividing. So if you have x and the uncertainty in x, and you need to add that to y and the uncertainty in y, how does that work? This is uncertainty plus or minus, of course, because it's random error. And so, how do you add something like that? Well, x plus y, and it's, combine the terms here. We have plus delta x, plus or minus delta x plus delta y. The plus or minus takes in, don't want too many pluses and minuses here. This takes care of the plus or minus. Plus delta x, delta y. This would be the value you're looking for, adding those two things together. The best value of x and the best value of y. In other words, we're a step beyond I got this value by measuring something several times. I got this value by measuring something several times. And I've got the uncertainties that you need to label whether that's maximum deviation or standard deviation. And it depends on how many data points you've got to find it. So the other thing I need to talk about now is hopefully no single error source in your experiment is going to be more than 10%. I mean, if you have a bunch of errors that are more than 10%, you can see that you're going to get an error that's way more than 10% for the answer when you start combining these things, which is what we're talking about. This is called propagation of error. How does the error propagate through of each individual value you've discovered experimentally? How does that error propagate through to the end, to the answer? So, and so if you add or subtract numbers, you add or subtract. I'll just stick with the add here. If you subtract these numbers, that would be a minus sign, of course. But this plus or minus takes into account whether it's plus or minus. So, if you have an error of 10% here and an error of 10% here, then the error in your answer is going to be pretty obviously 20%, right? Okay. So, and if this error is 2% and that's 5%, the error is going to be 7% in the sum or the difference. It doesn't matter. So, there's another thing. If you're designing an experiment and you have you get a value of like 7 plus or minus 1 and 4 plus or minus 1, and you have to subtract these to get the answer for some reason, you're going to get 3 plus or minus 2. That's a pretty big S, a 67% error in this number. So you don't ever want to design an experiment in which you have to subtract two numbers that are really close to each other, because you get a whopping percent error. So that would be a bad experimental design to avoid that. So 10% plus 10% is 20%. But 10% times 10% is 1%. So we can forget this, because it's a whole order of magnitude or more smaller than this number here. So your error then is the sum of the best values, the average values, plus or minus the sum of these are called absolute errors, because if you're adding apples to apples, you get apples, 7 apples, plus or minus 3 apples is 4 apples, whatever. And these are called absolute errors because these are in the same units that these numbers are, which is, of course, you have to add the same things or subtract the same things, because it doesn't make any sense to add or subtract different things. What's that mean? So these are called absolute errors, because they're the same units as these are. And plus or minus, doesn't matter, plus or minus gives you the same. You add the uncertainties and you get the error in the sum or the difference of two numbers. Let's take a look, and we're not going to do this very often, but that's how you do that, and you'll have a handout reminding you how to do that if you run across the case where you have two things subtracted in some kind of a big formula where you have other things multiplied or divided. Those are the multiplied or divided errors are the ones we're going to talk about next. So the errors in multiplying or dividing. Okay, so if we want to find the error in two things that are multiplied together or divided, and we will see, kind of like the plus or minus thing, the add or subtract thing, that the error either way is the same, as it turns out. And we can talk a little bit more about that if you want. So let's say we're calculating the area of something, and we know that would be the length times the width, like the area of this table. Excuse me. Now, let me not go through all the data acquisition that we did before. Let's cut to the values. The values plus or minus the maximum deviation or the standard deviation. So we get a value in x of 7.9 and the value of y. These are the average values that I get from averaging a bunch of data, and 6.2. And the errors here, and again, I don't know if this is standard deviation or maximum deviation. You have to state this. You have to go back and look at how they got the data. Are these 2 or 3 or 4 readings? Are these 52 readings? How many readings are there? That will tell you that what these numbers are, plus or minus the standard or the maximum deviation. And let's make that 0.3 and 0.2. So I'm just making these up, but these are averages, and these are your measured value plus your equals your average value plus or minus the deviation, whichever kind it is. Okay, so the question here, and the theory is a little bit more involved. I'm not going to get into the theory of it so much, but here we have to add fractional uncertainties, fractional errors. Okay, so that means we got to get the fractional errors. So what are these fractional errors? Well, for x, that would be 0.3 divided by 7.9. And for y, that would be 0.2 divided by 6.2. And if you calculate these, this is 0.04 and this is 0.03. Now, I'm getting some nasty numbers here. Of course, the better your results are, the smaller these numbers are going to be, the smaller your error range is going to be, and the smaller these numbers are going to be. So it could even be 0.00 something. So the smart thing to do, I think, is to convert these into not fractional errors, but percent errors, which means basically multiplying them by 100. Percent means per 100. So I'm going to convert these to percent, and that's 4 and 3. I like 4 and 3 much better than 0.04 and 0.03, especially when I've got to do crazy things like maybe square them and so forth. So the theory is, and we could spend a little time doing this, it's not too hard to see, but the theory is if you have error sources that are all below 10%, that the best value x times y is the best value, or the measured value, the best value of x and the best value of y. Obviously, that's the best value of the area, the average times the average, and then here we add, so that's equal to 7.9 times 6.2, whatever that is, we'll see in a minute, plus or minus the fractional sum of the errors, plus or minus 7%. Okay, so again, we're not adding apples and oranges here. We're multiplying masses times velocities, or masses times areas, or whatever we're multiplying these by. Each of these quantities, evidently, this means something physically. Lots of things mean something physically. Lots of combinations of things don't mean anything physically, so we don't use them. But length times width is area. That's a physical. Everybody understands that. So this is the best value of the area, which turns out to be 48.98 square whatevers, square centimeters, plus or minus 7%. So my answer is, taking these as the averages, these are the errors, converting those to percent errors, fractional errors or percent errors, that are a lot easier to work with, because those percents are usually between 1 and 10%, or maybe a little less than 1, but hopefully never any more than 10%. And so we get numbers that are pretty easy to work with, like these numbers. So one way to report that, so your best area, best experimental area is 48.98 square units, whatever those are, plus or minus 7%. Or if you want to write those again in absolute terms means you want to write them in terms of square centimeters, or square meters, square inches, square miles, whatever it is. You want to take 7% of this number. and you get plus or minus 3.42. This is 7% of this. And this is the percent version, and this is the absolute version. Maybe that makes you feel a little bit better. Okay, this is 49 square whatever, give or take 3. So that's something you can maybe makes the most sense to you instead of 7%. Well, because you probably want to say, well, what's 7% of 49? Well, it's 3. So this is probably a way to write it that makes most sense to most people, but this is fine also. So in the lab next week, we're going to be calculating the volume, this is the length times width times height, and you've got 3 errors, which you're going to convert into fractional errors, and then convert into percent errors, and then add the percents to get the percent error and the volume instead of the area. So we'll be measuring a block of wood. Okay, so unfortunately, the story's not over, but I'm going to put this number over here. Or 48.98 plus or minus 7%. Okay, those are my answers. I'm going to have to call that a provisional answer because we have another thing we've got to talk about, and that's significant figures. Okay, so let's do that. And as you get better at all this, more used to it with some practice, it will not seem so onerous and difficult and complicated and confusing. But this is kind of my provisional answer right now, and I've got to figure out basically how many significant figures can I put down to be honest about this. Okay, so here is, oh, by the way, significant figures. Let's just make sure you know about significant figures. Significant figures. How many significant figures does that have? I can't hear what you're saying, but I think you're saying 3. Okay, so how many significant figures does this have? I hope you're saying 1, because if you write this in scientific notation, it's 8 times 10 to the minus 3, right? Writing these things in scientific notation makes it very clear there's one real number there, and that's as good as you get. So there's one significant figure there. And but on the other hand, if you have 800, if you do an experiment and one chance out of 100 is going to be that it's an even 100 of something, 700, 800, 300. So if you measure that and you say, no, it's not 799, no, it's not 801, it's 800. It's not about 800, it's not 830 maybe, or 792, it's 800, give or take what? Give or take what is what we're talking about also. So this, if you maybe put a bar over that number, some people like to do that, that means, hey, I measured this and it's really, really close to 800, not about 800, or not 800, give or take 20 or 30. And so this would have 3 significant figures if you did that. So you got to somehow notate that, hey, that's 3 significant figures. Or you can put in parentheses to 3 significant figures. You see table. That's on quotes, in quotes, because it's, I don't know what else to call it. This column is going to be significant figures. There's 1 here. Okay. And this is going to be percent uncertainty, percent error, and we'll want to come up with, we want to make a little table here. So this is going to take a little explanation, but what if you have a number that's 1 significant figure? Okay, those numbers are 1 through 9. That's it. Okay. So I'm going to ask you what numbers, and subsequently what range of numbers round to 1? Okay, what range of numbers? What numbers round to 1? So what's the smallest number that rounds to 1? 0.5, I hope you're saying. Okay, so 0.5. And what's the largest number that rounds to 1? 1.5, I think I heard you say. Okay. And the range here, the range is 1. 0.5 to 1.5, the range is 1. Okay. Now, I want to ask the question, if the range is 1, if your uncertainty range is 1, which is what I'm saying, plus to minus, and the number is 1, if I have 1 plus or minus 1, what percent error is my uncertainty? 1 over 1 is 100%. And that's not too good. We hope that never happens. Okay. What if the number is 9? I mean, that's the biggest number. It could have one significant figure. And the range of numbers that round off to 9 are 9.5 and 8.5. And the range is 1. So the range is always going to be the same. Okay? So if the number is 9 instead of 1, this represents not 1, but one significant figure. If the number, one significant number is 9, then we have a range of 1/9, 1 out of 9, which is roughly, okay, it's picky, it's 11%. I'm going to say it's 10%. So if you have two significant figures, and the two significant figure numbers range from 10 to 99, okay, so two significant figures, and we don't have to have this discussion again, but what are the range of numbers that round to 99, 99.5 to 89.5, that's 1. What's the range of numbers that round to 10? That's 9.5 to 10.5, that's 1. Right, the range is 1. The range is 1 here, so 99, well, you get the point. So we have the same range of 1, but we have two significant figures. So what if the figure is 10? So 1 is what percent of 10? It's 10%. But what if the number is 99? 1 is 1/99th of 10 of 1. Not of 99, and we're going to call that, again, rounding off to 1%. Okay. And again, I think you got the idea, so we don't have to belabor this much more. We do have to go this far anyway. So the range is 1 for numbers that have 3 significant figures. The error in the range with 3 significant figures. And again, 1 out of 1,000, 1 out of 999, it is 0.1%, 1 out of 1,000, and 1 out of 100, that's the lowest 3-digit number, would be 1%. This is what we're after. So let me re-ask the question now that we've done this little calculation, and ask, okay, if my errors, if I add up my errors in the area or whatever it is I'm calculating, I have my grand total answer and my grand total error analysis, and I get those all done, and they come out to be 7%. How many significant figures can I honestly report? And the answer is 2. Okay, we'll come back to that over here and fix that up in a minute. And if I end up with a value that's like 0.5%, then how many, that's my grand total error and everything. That would be a pretty good experiment. We're going to run across 1 or 2 of those this semester, maybe, if you're careful. You got to be careful. Then you can report 3 significant figures. Now, this is an exercise in humility and humbleness, because I did all this work, and I did all this calculation. I got all those fractional uncertainties and percents and all that stuff, and added them all up, and I get 7%. But when I multiply 7.9 and 6.2, I get this nice 4-digit number. But some of those digits are not significant. because I just found that out, because this number is 7%. It's not 0.7%, it's not 0.07%, it's 7%. 7% of this number is 3. What that means is this number could be a number 3.5 higher than this, roughly, or 3.4 lower than that. It could be a number like 53 point something. It could be a number like 46 point something. I mean, you really don't know. You don't know. It's somewhere around 50. I mean, that's all you really know with this percent error. It's not that super accurate. So what do I do? Well, what you have to do is that this number here is important. 3%. Typically, we write the grand total error in one significant figure, and why that is what we're talking about. 3%. Okay, 3%. I should say 7% of this is 3, which means that this number could be like 53 something, or it could be as low as 46 something. So it's real close to a little bit under 50, give or take 3. Okay. So what this tells me is that these numbers here are basically insignificant, and that I have to round this off to the ones place, because that's where the error is. So we ignore this and look at the error to one significant figure, which is 3. Okay. So this has to be written as 49 plus or minus 3. And that is my final best answer. It includes the number, and this tells me how accurate that number is. It could be 3 or more. This is there is some uncertainty in the rules for uncertainty, I must say, but these are the generally accepted rules. So 49 plus or minus 3 is the way I would report square whatever the units are. Report my calculations based on the error analysis that I perform using standard or maximum deviations and so forth. So there's a lot more to this. Although it sounds like, oh my gosh, I got to do all that every time. Well, yes, but it will not get difficult. If you have an error that's over 1%, you have the choice of either 1 or 2 significant figures for your answers. As I said, it's a very humbling experience to do these experiments and realize that, hey, if I did this better, I have to do it a lot better to get down to 3 significant figures. Now, the National Institute for Standards and Technology, NIST, used to be the Bureau of Standards, has been measuring, and you'll be talking about this in class right away, your fundamental units of kilograms and meters and seconds. It's been measuring things to 10 or 11 significant figures. Imagine that. We can get 2 if we're lucky. If we're super lucky, we can get 3 sometimes. We only get 1 in this lab, even though we try to be very careful and do everything as carefully as possible. They get 11 significant figures. They need 11 significant figures because we need to know the accuracy of our fundamental units. The kilogram was recently, 3 years ago, redefined in terms of some fundamental quantities like the speed of light and so forth. And it's interesting reading to find out what that is. Using a current balance, which we're going to use next semester actually, but not quite that accurate. And in fact, I have to say this because I'm proud of this. One of our graduates was the director of the NIST, was appointed by President Obama. It's a presidential appointed position up until several years ago. Now he's the provost of the University of Pittsburgh. Anyway, so yes, coming from little Atchison, Kansas, Benedictine College in the middle of no place, you can go on to do great things. And he did, and a lot of our students did. So, feel good about yourself. Anyway, so typically we're going to end up in the 1 to 10% range, we hope. And so we can report 2 significant figures. So you have to round your answer back to 2 significant figures, and you have to round your error off to 1 digit, basically, because these make sense. These decimal places have to correspond to each other. You can't have 0.48 here. You can't have 48.98 plus or minus 3 here. But no, it doesn't make sense. The decimal places, the decimal place of the last digit has to be the same for the error and the number. You will have a handout that explains all this and gives you some examples. It's called the Propagation of Errors handout. And I want to give you a bonus. Probably don't want to hear anything more about errors, but bear with me. This is important stuff too. There is, as I said, some uncertainty and uncertainty rules. And if you have a like 1 point, if you have a yeah, all right. If the number's around 10, you might want to carry another significant figure. Now, what am I saying? I'm saying I got a list of numbers 10, 9, 8, and so forth. And this is 2 significant figures. This is 1 significant figure, and there's like a whole order of magnitude jump between 9 and 10. Is that reasonable? Is that exactly right? And so whenever you have a number that's around 10 or 11 or 12 or 13 or whatever percent, sometimes they put an extra digit there. So sometimes your percent errors, your total percent, final percent error can be 2 digits, but only if the first number is a 1, because it's still, it's a borderline between 1 and 2 digits. So, just a little bit of gravy there, I guess. Now, I'm going to go through this quickly, and I'm not going to try to even justify this, but we are actually overestimating errors. Now, this may be like a bridge too far or step too far or something. You're going to plug your ears and say it's over now. But let me just say this, because if you go into statistics and statistical analysis of errors a little bit more fully, you'll very quickly run across what's called adding errors in Quadrature. Quadrature. Okay. This is a really quick example. So you've done three measurements of whatever this is, and you've done 3 measurements of whatever this is, and you're multiplying them together like we just did to get the product for whatever reason you're getting the product. So this is 8 plus or minus 1. This is 5 plus or minus 1, right? The maximum error. That's all you can do when you have 3 data points. So the maximum error. So if you turn this into a percent, that's 13% or 12.5%. This is 20%, right? Because like if you're having to multiply these 2 things to get the answer, then it's the product stuff we talked about just a bit ago. And so the percent error is 13, and a percent error, this is 1/12, that's 1/5, so that's 13. So it's 33% error. Right? And I'm moving pretty fast. You can rewind and look at it again if you didn't get what I was saying. That's the beauty of this over lecture, I guess. But so 33% error. So it's 40. Say I have to multiply A and B, whatever I'm looking for. 40 plus or minus 33%, or 40 plus or minus 13, right? That's the absolute error, and this is the percent error. We talked about writing those both ways. So this is a pretty big fraction. It's a third of this number here, roughly. So that's kind of crude. Well, what's the point here? The point here is that if these are indeed random errors, that means that what we've done before to get the maximum deviation, we've taken the worst case scenarios and said that that's the range of our error. The worst case scenario would be 9 times 6 is 54, right? And the best case scenario, multiplying these together, would be 4 times 7, which is 28, right? And if you take the average of those, which is it's supposed to be around 40. This is a really crude example. You get 40 plus or minus 13 or 14. So that gives you 41 plus or minus 13. This gives 40 plus or minus 13, or 14 over there. But it's pretty much the same thing. Again, the numbers are really crude. It doesn't add up exactly. So it's 40 plus or minus, or it's 41 plus or minus 13. This is 40 plus or minus 13. It's pretty close to the same thing. So, excuse me. What we've done wrong here, and I hate to admit this because I just told you something that's wrong in a sense. We've taken the worst case scenario and the best case scenario, or the highest case scenario and the lowest case scenario, and said, that's my range of error, which is what we've done. And okay, that's fine. It's just to be safe. This is going to be the worst possible error in your answer, A times B, or X times Y. So, but what we've done, since these are random errors, why would you, if you measure something 3 times, why would you think that this number and this number have to go together? And this number and this number have to go together. Now, if you measure, you could measure at 9, and it could be, the other measurement could be 5 instead of 6. And you could measure 7, and the other number could be 6 instead of 4, and so forth. So you could pair them off this way. And you get numbers that are much closer to 40 on the average, and which have a much smaller percent range here. So here's adding errors in quadrature. Takes into account the fact that these are random numbers and these are random numbers, and why would you pair the biggest number here with the biggest number there every time, and the smallest number here with the smallest number there every time? You don't, because they're random numbers. So here's the error. Here's the error in A times B. The error in A times B, I'm calling it A. It's the error in A squared plus the error in B squared, the square root of those errors. You're probably pulling your hair out at this point, but that is adding these errors in quadrature, which basically, it's a rather complicated theory, says that, hey, these are random numbers. You don't pair the biggest one with the biggest one, the smallest one with the smallest one. You just take whatever you got. Sometimes it's bigger, sometimes it's smaller. Anyway, the range of the error, range of the numbers that you get by doing this random process is going to be smaller. And if you do this, I'm not going to do this, the square root of 0.20 squared plus 0.33 squared, you get something like 0.23, which is quite a bit smaller than we have over here. So your error here, and I'm just making that up. I don't know what that is exactly. So instead of 33% error, it's going to be more like 23% error, which takes into account these are random numbers. You don't pair the biggest one with the biggest one, the smallest one, the smallest one. You don't pair them at all. You take them as they are. And when you do that for lots of numbers, not 3, you get a much lower number here adding these errors in quadrature. So I put that on the back page of the propagation of error. If you really want to get brave, flip over the page, and there's the adding errors in quadrature page. So that's an example of how to do that. And you get a better example. You get a more accurate, honest representation of the error involved. Okay, thank you.